the impedance. Consider that in an AC circuit, a resistance and reactance are in series. The reactance can be a inductive reactance or it can be a capacitive reactance. Then we can find the impedance by this formula. R square plus X square, where X is the inductive reactance or capacitive reactance. Now let us consider that is RL circuit. There where is only resistance and inductance are present, and L is the inductance, L Henry is the inductance of this inductor, and then we can find by this formula we can find that inductive reactance XL equal to omega into L, and we can find the omega m, and then we can apply X can be replaced by XL. If there is a capacitive reactance is present, we can find the capacitive reactance with this formula 1 by omega c, and we can find it, and we can replace X by XC if it is a capacitive circuit, if it is a RC circuit. Now if both are present, if inductor and capacitor both are present in the circuit along with the resistance, then X will be XL minus XC, and if we replace X with that, then we can find the impedance. Now another very important for AC circuit analysis is that vector representations of sinusoidal waveforms. Now let us consider a circuit consists of R, L and C in series, and this has been supplied by a sinusoidal voltage waveform V, and as a result a voltage VR is generated across R, VL across L and VC across C. Now all these voltage are of sinusoidal in nature, and we'll draw a phasor diagram of these voltages. Now you can see that first VR will be phased with current I. The common current is flowing through all these RLC. Therefore, R is voltage across R is in phase with the I. Therefore, I am showing here there is a VR. You can see this is the I. Therefore, it is phased with I. And you can see I am representing from, you can say this is 0 to this, it is a VL. Therefore, you can see the VL. It is the voltage across L is ahead of 90 degree of I. What is the current I is flowing? The voltage across L, it is leading the current by 90 degree. On the other hand, the voltage across C is lagging the current by 90 degree. Therefore, you can say the VL, this VL and VC are completely in phase in oppositions. One is completely opposite to other. Therefore, you can see this is the 0 to VL I'm showing here, and this is the VC. And therefore, resultant voltage will be subtraction from one to another. Therefore, here VL is greater. Therefore, resultant will be VL minus VC. Therefore, I am showing here VL minus VC is represented by this vector. Then now, this resultant vector, if we find this result, this VL minus VC and the voltage across R, we find the supply voltage, the vector summations. We can find the supply voltage here, and it is the phasor diagrams of these voltages in this circuit. Now you can see the resultant voltage which is then applied to the RLC circuit, and these voltage and the current generated, there is a phase difference of phi, and this is called the phase angle, and cos of that is called that power factor of the circuit.